Hello, everybody. Welcome to the next installment of the DeepWave Digital Webinar series. Today we'll be discussing the detection and labeling of training data for signal classification problems in deep learning. So in today's webinar, we will be covering the Artificial Intelligence Radio Transceiver, ART, that is DeepWave's main product line. We'll also be discussing the basic concepts for using cuSignal for GPU signal processing. If you're not familiar with it, cuSignal is NVIDIA's GPU accelerated signal processing library that is maintained by the RAPIDS group at NVIDIA. We will then be going into a software source code deep dive where we will create a pulsed signal detection, plotting, and recording software suite. We will use this software suite to detect over-the-air transmissions from 10 key fobs that I have here. Those are shown in the top right-hand corner. They range anything from Ford truck key fobs to Jeep to Hyundai to Chrysler. So what you need to understand and be able to follow this webinar is a basic understanding of Python, a very basic understanding of object-oriented programming in Python, and then an ART to execute the software and to receive the signals over the air. All of this will be provided in the form of source code, and that is available on the DeepWave Digital GitHub site in the webinars project. So if you look in the bottom right-hand side, we are showing you a visualization of what the software that we will be building up in this webinar will do. This is a key fob signal that is received over the air, and the amplitude as a function of time is shown in the top plot. That is a complex valued signal where the green is the real part and the orange is the imaginary. On the bottom plot, we have the power of the same signal as a function of time. And you can see that this looks more like a square wave. And we put a constant threshold, which is the white dotted line on the bottom plot. And that white dotted line, should any of the power in the signal cross that threshold, that signal would then be recorded to disk. And you can see that in the by the fact that certain segments are colored blue and teal, and those blue and teal segments are in fact recorded to disk. So we'll be walking through from scratch how to create this code base. But first, let's start with an introduction to DeepWave Digital. So what we do is we create hardware and software products to enable our customers to develop and deploy artificial intelligence algorithms within RF and wireless systems. This can be anything ranging from signal identification to interference mitigation, electronic protection, any of the above. So where we really live and where our core competency is at the intersection of wireless systems, signal processing, and deep learning. Our customers range from anything from wireless OEMs to defense contractors, and we are headquartered in the city of Philadelphia in the United States. So there are many challenges that are facing the RF systems and signals community, ranging anything from congested spectrum for cognitive radio, electronic attack or jamming, anti-jam features. All of this are very challenging problems that face the RF community. And DeepWave Digital is not claiming that artificial intelligence and deep learning is going to solve all of these problems. What we are saying is that there exists an intersection where we have a complex problem, and that problem does not have an analytical solution. When this happens, that is the area where machine learning can really be applied and utilized to its full potential. So to deploy a neural network on the ART, we have a three-step process. But prior to that three-step process, you have to have training data in order to be able to create your AI algorithm. And that is what we're going to be covering in this webinar. We are covering the acquisition and labeling of training data. But once you have that, what do you do with it? Okay, so the first thing you do with it is you train your neural network. So you choose your AI framework. If you're going to be using the AIRT for deployment, it can be anything ranging from TensorFlow to Caffe to MATLAB. We pipe our data through our neural network and then we train it and we end up with a trained network on the other side. But that trained network is not optimized. In fact, it is unoptimized. So then we run it through NVIDIA's TensorRT library, which takes an unoptimized neural network and fuses layers together, optimizes precision and a lot of other things in order to come up with a plan file, which is an optimized neural network. You can then take that plan file and deploy it on the AIRT, on DeepWave's AIRT. So we support that plan file, and so therefore we inherit the support for all the different frameworks associated with training neural networks. Okay, so here is what we're going to be discussing today. The first thing we're going to talk about is the AIRT hardware system. And then after that, everything's pretty much software based. So after we discuss the AIRT system, then we'll go over AirStack. AirStack is the software stack on the AIRT that is used for programming the system and updating the hardware parameters. Then we will go into some basics of signal processing with cuSignal. We'll talk a little bit more detailed than we did in the last webinar and some specific things that you should look for in order to be able to optimize. Then we'll go into a deep dive of building our power detector signal recording software stack for recording training data, and then we'll provide a brief summary. So DeepWave's artificial intelligence radio transceiver, AIRT, is an edge compute AI platform for radio frequencies. So you can think of it as a software-defined radio. So it's got a transmitter, it's got a receiver, can tune to various frequency range. And embedded on that is all of the processing power needed for deep learning. And so this is a product that gets deployed out in the field. It's edge compute, so it goes in the tower, on the drone, on the side of a building, wherever the signals are retransmitting and receiving. Accompanying the AIRT is a great software stack called AirStack. So looking at the software stack from the bottom up, you have your AIRT hardware, then you have the operating system and firmware that comes preloaded on the AIRT. Then we have our drivers that allow the user to communicate with the RF front end. Then we support all of the major signal processing and deep learning libraries. And then on top of that, we work very hard to make sure we have Python abstraction layers for all of the signal processing and deep learning libraries. We don't write all of them. We contribute to some, we write some, but the bottom line is that we are making sure that the system is easy to program. You get the speed up of C++ and CUDA, but you're writing it in Python. You can program on the CPU, the GPU for signal processing, and neural networks, we recommend executing that on the GPU. So the left-hand side of this slide shows a rendering of the AIRT, and the right-hand side shows the accompanying block diagram. So the signals come in through the antenna ports, and those on the rendering are shown here as the metal ports. The signal then goes to the RF chip, which is the Analog Devices 9371. This is the RF chip on the rendering. The samples are then sent across a JESD bus to the Xilinx 7 series Artix FPGA. That is shown over here in the maroon. And then from in the FPGA, the decimation, basically the changing of rates happens. So the decimation or interpolation. And then that signal is sent across, is DMA'd across the PCIe bus to the memory on the NVIDIA Jetson TX2. Now that NVIDIA Jetson TX2 has this very nice feature of having shared memory between the CPU and the GPU. That is very important for real-time signal processing because that eliminates the extra memory copy that is typically associated with doing GPU computation. This Jetson has 256 GPU cores and 6 CPU cores. It also runs Ubuntu 18.04, which means that you don't need an accompanying laptop or desktop computer with the software-defined radio. It has the computer built in. And so therefore you just plug in your keyboard, your mouse, and your monitor, and you're off and running. So I mentioned the shared memory architecture, and let me explain real quick why that is so important. So on the left-hand side, I have a traditional software-defined radio that you want to use to do GPU signal processing. So you want to do highly parallel wideband signal processing on the GPU, but your software-defined radio doesn't have a GPU built into it. So what do? Well, you have your transceiver subsystem over here, and then memory gets signals get transferred to and from the memory on the CPU. Because the GPU does not actually see the system memory for the CPU, you then have to do another transfer over to the GPU memory, which adds extra latency. Now, for the AirT, we have a much nicer architecture where we have the transceiver subsystem directly writing to and reading from the shared memory where the GPU and the CPU have equal access. So they can actually access the memory without that extra copy, which can, depending on your application, reduce latency up to 50 milliseconds. The AirT comes in two variants. There's the 7100 series and the 7200 series. Both of the variants have the same radio front end, the same CPU, the same GPU. They differ by the FPGA. By upgrading from the 7100 to the 7200, you end up with more than double the number of logic cells, about 5 or 6 times the number of DSP slices, and about 4 times the number of amount of memory. So it's a pretty significant upgrade to the 7200. We now have those in stock. That is a new product. So contact us if you are interested in that product. Okay, so now let's talk about the AirStack software API. So you've already seen this. So the AirStack API or software stack is shown on the left-hand side. And what we're going to do is, you may have already seen this in our last webinar, but I'm going to walk through it real quick. And I'll go ahead and populate it. So what we're going to walk through is the different ways you can do signal processing or deep learning on the various architectures on the AirT. So if you want to do CPU signal processing, you can leverage SciPy.signal, NumPy, or GNU Radio. If you want to leverage the GPU for highly parallel processing, you can leverage CuPy, Numba, PyCUDA, CUDA itself, or cuSignal. And then for neural network inference, TensorRT directly or GR WaveLearner is our open source GNU Radio framework for deploying neural networks within GNU Radio. So today, what we're going to be talking about is processing the signals as they come in to detect them, to look for key fobs. And if we find them, then we're going to record them to disk. And we're going to do all of this by leveraging CuPy and cuSignal and also some Numba. Here is the AirT that I will be doing the demonstration with. So here is the front of the AirT. We have our RF ports, which contain transmit, receive, synchronization, 10 meg reference, a local oscillator. When powered on, the on button illuminates. Here's the back side. So I mentioned that it runs Ubuntu, so it is a computer. So power comes in. I have a wireless USB mouse there, a keyboard and mouse. This is the HDMI and this is Ethernet. So I'm going to be using the Ethernet because that's how I'm going to be showing you the display. I've got a no machine instance running on the AirT, and that allows me to do a virtual interface to it. Okay, so let's real quick walk through the code that I did in the last webinar, which is the very basics of how you write code for the AirT. So this is Python. We leverage the SOAPy SDR API. SOAPy SDR, look it up on GitHub. It is an open source framework for software-defined radio. It allows people to write plugins for SOAPy SDR, and then you get to leverage this much larger ecosystem of software-defined radios APIs. So we have written a SOAPy AirT plugin, and so essentially you use the SOAPy SDR API to communicate with the ART. So after we import our packages here, then we define our RF parameters. So we're defining channel 0, we define our buffer size, which is 16384, the sample rate, the tune frequency I set to 750 megahertz. And in this instance, we are going to use the AGC. AGC stands for auto gain control. So the ART will apply gain according to the input power level. Next step is to initialize the radio class. So we are setting the sample rate, setting the gain, setting the frequency. And then we need to create a buffer to stream data from the radio into. We're calling that buff. It is of size n. Then the next thing we do is turn on the radio. So after line 22, we are now streaming samples to the buffer, and we need to read them and do something with them. The next thing that we do is read stream. So we're reading samples from the buffer. And then we need to do something. We're reading samples to the buffer, I'm sorry. And then we need to do something with them. So this is kind of a dumb application here because it's not very useful. It doesn't have any application. So after you read the samples into the buffer, we don't do anything with them. We just read the next one. So what you would do here is you would insert your application, and that is what we'll be covering here. What does that application look like for power detection and writing to disk? And then finally, once you're done, if you hit Control C, you'll get into this exception here, clean up whatever you need to do, close files, whatever, and then exit. And then the radio turns off. Okay, so now let's go through a little bit more detail than last time into signal processing with cuSignal, a couple of tricks that we need to learn. Okay, so cuSignal is an open source API that is maintained by the NVIDIA Rapids team. It expands on the popular scipy.signal library to GPU accelerate that code. So the code base is written using CuPy as a drop-in replacement for NumPy. When necessary, it leverages raw CUDA, CuPy, and also some custom Numba kernels to get additional acceleration when we need it. One very nice feature of it is that it enables a streaming interface with zero copy. So zero copy is how you leverage the shared memory architecture on the ART. And this also allows us to never have to transfer things from GPU memory, even if we're doing deep learning, like leveraging PyTorch. So they have a GitHub with cuSignal. It's all open source, and documentation can be found at the website there. So installing cuSignal on the ART, go to the easiest thing to do. It gets updated regularly, docs.deepwavedigital.com. This particular tutorial is screenshotted over here, shows you how to install cuSignal on the ART. cuSignal is mainly supported through an Anaconda environment. Anaconda is a virtual Python environment, if you're not familiar with it. So essentially what that means is it creates a sandbox for you to install Python packages without potentially messing up the base Python package for your operating system. So we provide a YAML file which has all of the packages that need to be installed for cuSignal. You create your Conda environment, and then once you create your Conda environment, you clone cuSignal repo, and then you install cuSignal, and then you're done. Okay, so let's look at some cuSignal code. So I mentioned that one of the nice things about cuSignal, in particular, we're talking here cuSignal and CuPy, is that it's just a one-to-one replacement for familiar toolboxes like NumPy and SciPy. So what this code does is it has the same basic infrastructure as the radio code that I showed you earlier, except what we are doing is we are adding an application in here, which is the irrational resampler. So let's walk through this real quick. So we import our packages here. We're importing NumPy and scipy.signal. We're going to define our parameters there, same ones as before. But we're now going to create a polyphase filter. So this is a rational resampler. So first thing we're going to do is we're going to create a FIR filter. and then we're going to instantiate a signal resample poly. So that is a SciPy signal polyphase rational resampler. So it's going to change the data rate. It's going to upsample by 16, apply a FIR filter, and then downsample by 25. We create our buffer there just as we did before. This is a NumPy array, so we're just going to use NumPy for the buffer. We are going to turn on the radio and start streaming, and then we're going to execute our application. So we come in here for in reads. We read the data, we transfer the data to the buffer. If the return is -4, that means we dropped data. We weren't able to process fast enough and the buffer overflowed. That's nice to know. And here we just count whenever that happens. And then we apply to the buffer, we apply the polyphase rational resampler, and then we're done. We're calling that our application in this instance. And then we measure the data rate and get out of here. So this is the code that you're probably familiar with. This is how you would do it in Python. This is how easy it is to now do a GPU accelerated version of that. We just substitute CuPy for NumPy. We substitute cuSignal for SciPy.signal, and then everything else is a drop-in replacement. There's really nothing else that changes except for one line, and that's this green line, line 14 on the cuSignal side. We need to make sure that we tell the system that it needs to do multiplication on the GPU, not the CPU. Otherwise, it might accidentally unknowingly choose the CPU. And the way we do that is by calling CuPy as array of the window. So we're just saying anything that has to do with the window, do on the GPU. That's really it. Super simple. And the beauty of this is simply by changing those things, we get an 8x speed up on the AIRT. That is extremely significant. So all of this was discussed in the last webinar. I highly recommend seeing that if you want a full understanding of this code and a demonstration. Moving on, today what we're going to talk about is a couple of little bits of information that will help you accelerate your GPU code very, very easily. So what I'm showing here, so what I said that we're going to be building up here is a power detector followed by writing the detected segments to disk. So so the first thing you got to do for a power detector is to measure the power. So how do we do that? Well, for a complex valued signal, we can do it a bunch of different ways. And here I'm going to show you 3 different ways. So the first is just to do the real part squared plus the imaginary part squared. The second way is to do the absolute value squared, or you could do a conjugate multiplication. But what I want to emphasize is that if you're just going to do native Python math, like 1 times 2, and you don't explicitly tell it to execute that on the GPU, it might choose the CPU and you don't know it, and that would make your code a lot slower. So we'll show you how to explicitly say, hey, do this on the GPU. And then we have another aspect is that you can either specify to do it explicitly on the GPU, or you can just use a GPU library, and that of course will be done on the GPU. So let's walk through this code. So what we're doing here is we're going to calculate the instantaneous power of a signal 3 different ways and benchmark them. Okay, so we import our packages. We create a buffer, and we're going to read the samples from that buffer 1,000 times. Here we're not actually going to have the radio on because I don't want to be limited by the data rate of the radio. If we have a hardware clock in the test, then the fastest we could ever go is that hardware clock. So I'm going to emulate it. And so the way I'm doing that is I'm creating a test signal, and then I create a test buffer, and I just populate that buffer with the test signal as opposed to populating it with the data coming off of the radio front end. So for test 1, the way we're calculating the power is the real part squared plus the imaginary part squared. That is the power calculation for a complex valued signal. So then we're going to read 1,000 times. We're going to populate the buffer, the shared memory buffer, mind you, with the noise signal. We're just going to do that over and over again. And every time we do that, we'll calculate the power. and then we'll report a data rate. And when we do that, we get 34 megasamples per second. Now that's not very high. That's pretty high for a CPU, but it's not very high for a GPU. And the reason why that is slow is because this is just basic Python math. We didn't tell it to execute that on the GPU, and so therefore it just did it on the ARM processor, and that ARM processor processes at about 34 megasamples per second. The next one, we actually specify to do it on the GPU, and that's the same way we did before, is by calling cupi.asArray of buffer. Now this doesn't actually do a transfer or a memory copy or anything, it just makes it a GPU, a cupi array. We then, in the for loop, we read the noise into the buffer. We then say, hey, the buffer is in fact a cupi array. And then we do the same computations before, but you can see the speed up there is significant. We went from 34 megasamples per second up to 255 megasamples per second. Lastly, instead of saying, hey, do this on the GPU, we're just going to use the GPU library directly, which is cupi. Now we could have done cupi power squared, but here we decided to do cupi power squared of the absolute value. This is mathematically equivalent to this up here for a complex valued signal, so we can just do that. And you see for this particular test, we're running close to 300 megasamples per second, which is significantly fast. In fact, you can see that the speed up from method 2 to method 3 is greater than the maximum data rate in method 1, which is on the CPU. Point of this slide, make sure the computation that you're doing is being done on the GPU, if that's what you want. So the next lesson learned is that the Python interfaces to interact with cupi and cusignal are high abstraction layers for the for CUDA code. Okay, so what that means is that a lot of things tend to be compiled at runtime or as needed, and that can create additional overhead. And if you don't do it properly, then that can make your signal processing application slower than you meant to. And so looking over here at the right-hand side, exact same code to line 17 as before, so I won't go through that again. And then we're going to be doing two methods here. This method, we start our timer, we read the test signal into the buffer, and then we calculate the power, and we do this 1,000 times, and we get 254 megasamples per second. Now look at this one, where we all we did up here was do that computation one time before the for loop, and we got almost a 50, we got like a 45 megasample per second speed up. The reason why that happens is because cupi is creating a CUDA kernel right here, and then it's reusing that CUDA kernel in the for loop. If you don't have this prior to the for loop, then it's the first time it's run, it is that CUDA kernel is compiled, and that takes away from your time stat, and that is not something that we want because we could have dropped data in that circumstance. Okay, so those are two things that you need to keep in mind, and that will take us into our very first demonstration for this webinar. Okay, so I mentioned before that we have a no machine instance running on the AirT. So what that gives me is a virtual display over Ethernet for my AirT, and that's what I have right here. So this is actually operating on my AirT that is sitting next to me. And so let's look at that. Okay, so all right, so here we go. So I have the same codes that I've been walking through on the PowerPoint over here on the AirT. So this is the CPU versus GPU benchmark. So this is the 3-test benchmark where we looked at accidentally doing the computation on the CPU and then doing the computation on the GPU by declaring a cupi array and then using cupi power directly to force the execution on the GPU. And so I will run this. So the first thing that we need to do is enable our Conda environment. Now, on this particular system, I have multiple Conda environments because I am doing development. So the Conda environment, I'm going to specify the the cuSignal version number. So do Conda activate cuSignal 0.14. Okay, so now I'm in my Conda environment. Let's see what directory I am in, the correct directory. So I am going to execute the power bench CPU versus GPU. Okay, so now we're starting to get our benchmarks. And you can see fairly similar to what I showed in the on the PowerPoint slides. So method 1 is execute on the CPU, and that's the slowest. And then we have our 2 other that are comparable. It's worth noting that the AIRT runs at 125 megasamples per second. Both of these top 2 would be able to handle that. Okay, and so let's look at the second benchmark that I was showing. So this is the one where we are showing the difference between compiling the CUDA kernel first and not compiling the CUDA kernel first. So if I do that, so I'll open up a new terminal and we will do, okay, and I'll do conda activate cuSignal 0.14. All right, and then now I'm going to execute. You can either do a / if you make it executable, or if it's not executable, you can just do Python compile to this test. Okay, so that's running now. All right, so we're starting to get results. And we see that the method 2 is ever so slightly faster than method 1 here. Alrighty. So let's go back to our presentation. Okay, and so now let's look at the more detailed version of our detector algorithm. So we've done our benchmarking, now let's actually write the code. So here is the setup that we're looking at. So we have our key fob over here. A key fob is going to emit a signal. It's going to come into the AIRT's antenna. And then we are going to, if the signal crosses our detection threshold, we're going to display it over here, and we're also going to record that to disk. Now we're only going to record the segments with detected signals. So if your application requires signal streams with and without pulses on, then you're going to have to adapt this, but it's a great starting point. And we have these 10 key fobs that we're showing here. So the code base that we're going to walk through, the main Python function is called detect and record.py. Now detect and record.py depends on 3 classes, 3 Python classes. And so those 3 classes are power detector, which takes in the receive signal and detects for the pulses. Then we have our detector writer, and then which writes to disk, and then we have our detector plotter. So we're going to walk through each of these. So the first one is it's a Python function, and it sets up the receiver. It creates the memory buffers. It reads the signal, and then it runs those 3 classes. The first class is power detector. So power detector sets up the FIR filter. It calculates the instantaneous power. It then low pass filters that instantaneous power and brings it down to a lower data rate for thresholding. We then compare that power level to the threshold. We also have an M of N detector in there as well. and then we return the segments that pass the threshold and the M of N detector. We then write those segments that were detected to disk. We can specify the max number of files to write, and then we print how many files have been written to standard out. So if we write the number of files desired, then the system will exit. And then every time, if desired, if you turn visualization on, then if desired, we will display the plot that you saw before, where the top plot is amplitude versus time and the bottom plot is power versus time. Okay, so let's walk through these. So the first thing I'm going to walk through is the help menu for detect and record. So I mentioned all of this is on GitHub. You can or soon to be on GitHub. You can download it. So for detect and record, the only required argument is the label. So if we have a key fob that is a Chrysler, maybe that's label 1. We would call this label 1. We then have to. We can then specify a bunch of optional parameters, which all have defaults. So you specify the number of files, that's default to infinity, so just keep on going. The segment length. The segment length is the number of samples per file. And so what that means, and that's typically your neural network and the width of your input layer on the neural network. We can then specify the sample rate. Since the key fobs are relatively low bandwidth, we're using a pretty low sample rate of about 8 megahertz. Specify your threshold. So the maximum power level that you could have is 0 dB because that is the maximum input power. That's full scale. Set the frequency, set the channel, set the gain. It defaults to AGC, but you can put a number in there. The buffer length, here it's 32,768. If you're doing a lot of computations, you can make that larger. The decimation factor, now recall the decimation factor is applied to the power signal, not the amplitude versus time signal. You do a -V if you want to visualize it, and then you specify an output path. Okay, so here is we're going to walk through this code. So here we're looking at detect and record. So I had to split it up into 2 columns. So line 60, so this actually goes underneath here. So it's just a continuation. So what this code does, so after we import all of our packages and after we set up our command line arguments, the first thing we do is set up the receiver. You've seen this before. Next thing we do is create our buffer. You've seen that before. Then we have our detector, our writer, and our visualization set up. So recall that you want to call all functions prior to the actual execution where you're streaming data. So that's what we do here. So we instantiate our detector. You'll see in a second within that detector class. The first time when you initialize it, it does in fact call the functions the first time to create the CUDA kernels. We then instantiate our writer class, so we feed it the output path, the label, and the number of files to write. And then if we want to visualize, then we set up the plotter class. And then we're over here now on the actual execution. So we turn on the radio, and then we're in our infinite loop, and this infinite loop receives a signal. If data was dropped, it prints an O. If you recall before, I said if the return is -4, then data was dropped. Well, there's actually a parameter in SOAPy SDR that lets you know that just in case that ever changes in a future release of SOAPy SDR, it is now a constant that's defined in the API, so we just compare it to that from now on. If data was not dropped, then we send the buffer to the detector. We then, and the output of that is the signals that are classified, or the segments with signals that pass the threshold. We then send the detections to the file writer, and then if desired, we visualize. So we'll show that plot. If you press Control-C, you'll deactivate the streams and break out of here. So one thing I do want to note is that the visualization plotter cannot keep up with the full data rate. So you will, in fact, drop data if you have visualization activated, but that's not that big of a deal for recording training data in this circumstance because that just means I have to hit the button more times in order to get the amount of data we want. And in the real world, if you were doing inference, say, you wouldn't want to do that because you might miss the signal you were looking for. Okay, so that's the basics for the main function. So now let's look at our classes. If you are not familiar with object-oriented programming, it's probably a good thing to start looking into that for programming on the ART because Python is a very object-oriented language. So essentially you create classes, and classes have properties and methods and attributes and all sorts of things that kind of stay within that class. So we have our power detector class. When we initialize our power detector class, we create all of these properties or variables that are associated with it. So anytime you call the power detector class after that, these are kind of constant in there. So we set up a bunch of things, including our filter window. So we have an internal function to the power detector class called create fir filter window. All that does is exactly what it says. It creates a fir filter window. And notice that we made that a CuPy array. Because it's called in the initialization block, it's called that first time, and we never have to call it again. It's just stored there in memory. And then we're initialized. Then there is a method called detect. So the detect method is the meat of the class. It's the main part of the class. So what we do here is we calculate the power level as you saw before. So that's power as a function of time. We then run through cuSignal decimate. So we can pass decimate in a fir filter window and a decimation integer. And it will, in fact, filter and downsample the data. We then reshape the decimated data into a 2D matrix of width segment. So we basically are breaking it up so each row is a segment. We then compare every power level in that matrix to a threshold. And then we sum the detections for each segment and see if the number of detections per segment is above the variable required sample is above threshold, which is set up here as 4. If that happens, so this is kind of our pseudo M of n detector. So in this instance, for a segment to be considered having a detection, you have to have or you have to have more than 4 samples above threshold. So that helps keep down false alarms. And then once that's the case, we then have a Boolean array that tells you which segments have signal in them. We then reshape our original signal and return our original signal, X, our original signal. We then reshape it into segment lengths and only pass out the detection rows. So what you get back is each row is a segment to be recorded to disk, and you only pass back the rows that had signal. And you'll notice that I didn't just tell you this stuff about compiling the CUDA kernels for the fun of it. We actually have to do that here. So when we run our initialization class, the last thing that we do is we run the detect block, and that forces the execution of all of this code. And if CUDA kernels are being compiled, they are now officially compiled. You don't have to worry about that in detect in the main loop. You only have to, the class itself takes care of it. And then we've got our other thing over here where we are, in fact, doing CuPower as opposed to the real squared plus imaginary squared. Okay, so we did also create a benchmark. I won't run this live in the interest of time, but we did create a benchmark for the power detector class. You've seen all this before. we instantiate the power detector class here. We put it in the same timing loop that we've been doing the whole time. Um, and then we measure it. And we measured it on the AirT, and that gets 155 megasamples per second, so no problem at all running real time. And then just for fun, we took the exact same code and ran it on our training server, which has a Pascal, a Tesla Pascal GPU on it. And without any code modifications, got almost 600 megasamples per second. So that's like 600 megahertz of bandwidth. That's pretty good. We could probably optimize this and get more, but it just wasn't worth it. The next class is the power detector writer class. Pretty simple one. We start it up, and all this does is create the directories to write the files to. Starts a file counter, because if you specify the max number of files, I need to know when I have exceeded that. Then we have a simple method called toFile. It simply just comes in here through your detection signal matrix, writes each row to a file. So each row becomes its own file. And then if you exceed the max number of files, we exit. And if it's the last row in the matrix, then we just tell you how many files have been written so far. I am not going to go over the power detector plotting class. It is pretty, as with any data visualization code, it's hard to walk through over PowerPoint because there's a lot of little minor details. But suffice it to say that what happens is we create our axes, and then instead of replotting our axes each time, we just update the data and redraw the data in those axes. So that helps us save time, helps us get a little bit more real time. But as I said before, it does not actually run real time. You will drop data if you run this, and that is to be expected. Okay, so this is what it's going to look like. So now I will run the last demonstration of the day. Okay, so let's make this full screen. All right. Okay, so what I'm going to do is switch desktops. I'm going to come over here to this one, and I already have it set up for me. So what we're going to do is run detect and record. I am already in my cuSignal environment, as you can see. We're going to run detect and record. And if you recall, you have to pass it a label. The label that we're giving the key fob that I'm using right now, it's a Ford. And I have stickers on the back of all of them. And this one is labeled 2. I'm going to record 2,000 files. I'm going to have the visualizer on, and then we're going to output it to an SSD drive that I have attached. We're going to put it in the recordings folder. So I'm going to hit go on that. Okay, so any second now, it should start up and be looking for signals. Okay, so now we're looking for signals, and I'm going to hit the button now. All right, so now we can see the key fob signals coming in. And we got 943 signals or files out of that one button press. And you can see that we did in fact get an overflow, as I mentioned, that is expected because we are plotting. And the plot is blocking. So I'm going to hit it again because we need to get up to 2,000 files in order to exit. My guess is I'll have to hit it one more time after this. Oh, I didn't. So 2 button presses got us 2,000 recorded files. And now we have a small set of training data for a Ford key fob. So next we are going to do the same thing, but I now have a, let me see, what is it? It is a Dodge key fob, which is number 6. I guess I could have done them in order, but I did not. So detect and record 2,000 samples, visualize, and we're going to write it to the same directory. Okay, so any second we will be receiving signals. All right, so now we are looking for signals to record. The best part is look at the utilization of the GPU on the bottom. Um, we're processing this. It's a relatively low data rate, so it's really not taking up hardly any GPU. So I'm going to hit the button now. So what that means is that we have plenty of room here to also do neural network inference simultaneous with this. So now I'm going to hit the button. Um, yep, it's a much different looking signal. We got 1,007 files out of it. So that was the lock button. Let's try the panic button. Panic button. And boom, 2,000 files written to disk. Okay, it was that easy. And now let's look at um, our data drive recordings. Look at that, 2,000 files, and it put it in the proper label. And then we could just point AirPack or whatever neural network system you have here. It gives it the label and then increments the number. They're all the exact same size, 256 samples. Okay, so that concludes the demonstration portion. So now we'll go back to here. So let's talk about our next webinar. So what we did today was we recorded training data. We showed you how to do all of the processing using cuSignal to do real-time acquisition of training data and labeling of that training data autonomously. That is very useful. And that sets us up perfectly for the next webinar, which is taking that data and all of the lessons learned from the previous two and actually creating a neural network for classification. So the way we're going to do that is we are going to demonstrate AirPack. AirPack, if you're not familiar, check out the website there, but it's basically everything you need, including the source code, to teach engineers the crucial steps for classifying RF signals using a convolutional neural network. So the data that we just obtained could easily be used to train AirPack. So we'll walk through that, and we'll walk through a little bit on how to prepare data like we just took to make it more real world reliable. For instance, adding things like channel models and noise and jamming and all that stuff to it we'll cover. So date to be announced shortly. So sign up for our mailing list or follow us on Twitter. And we will be announcing it as soon as we have that date set. So just to kind of summarize, our main product line is the artificial intelligence radio transceiver. We have two models of that, one with a larger FPGA and one with a regular size FPGA. We are going to be releasing a rugged version of that soon, and this comes with our AirStack development environment. Accompanying the AirT is AirPack. AirPack is a comprehensive software solution for creating AI-enabled signal processing applications. So we include the training data, the source code, the neural network, basically to try and reduce the level of engineering effort for everybody out there to learn how to do this. So we're basically lowering that barrier to entry there, taking it from a month down to days. So feel free to contact us. You can contact us either via email or fill out an inquiry on our website. And so with that, it looks like I have time for one, maybe two questions. So you should be able to ask questions in the comment bar, and I will get to them as I can. And if I cannot get to them, I will follow up, or you can follow up with us. All right, thank you and have a great day.